All right, welcome. Let's begin. Um, so Wednesday you've got homework number 12, which is due, and then the week after that, so Wednesday of next week, the project is due. We've already talked about what the spreadsheet should look like. We've already talked about the write-up. So hopefully you're making good progress on that. Today we're going to continue talking about some techniques and tools that allow us to do cost estimation. And so all of this continues to come from chapter 15 in the book. I've gotten a couple of questions from people who are asking, like, how can I improve my grade, or do you have study suggestions for the final exam? And so I think if you haven't already got a copy of the book or an old edition of it, which is mostly the same, it would be worth grabbing one. You'd maybe use it as a reference in the future after you finish with the class, but then even before you finish the class, I think reviewing some of the explanations that are in there for a handful of the trickier concepts we've had this semester would be worthwhile. So I think when I looked last time, there were old editions of the book available for as little as $20 shipped. So I think that's money well spent. So today we're going to do an in-class exercise that has three components to it. One is related to cost capacity equations, and then the factor method and activity-based costing. And so these are all kind of just the accepted techniques that are talked about in the first part of this chapter, where the quality of your cost estimation is based in large part on the applicability of the data and your adherence to accepted techniques for generating cost estimates. I don't like the sound of that. It always makes me worry that I'm losing my microphone. Seems like it's still good though. Who knows what's going on. All right, so let's get into it. Something's locked up. Okay. In the homework assignment that you've got due on Wednesday, I wanted to give you just a hint on how to calculate the total cost. This is the formula that you should use, and we'll talk about this today when we're talking about indirect cost recovery and the factor method. But the basic idea is that if you know the cost of a major component of an overall project, then you can find the total cost of the project as a function of that major piece of equipment. But then there's additional costs that are added on top of it. So if C sub E was the cost of a major piece of equipment, and then there are some direct cost factors. For instance, if you're buying an electricity generator, like a backup generator that's going to be installed at a hospital, then the cost of the generator would be the biggest component of the expense. But then you might just, as a rule of thumb, say that whatever the cost of the generator is, you need to allocate 25% extra to cover the cost of installation and preparing a pad for the generator to be placed. And so those are direct cost factors. So you add up all of the direct cost factors and then multiply those by the cost of the major piece of equipment. But then on top of that, you have to add indirect cost factors. And indirect cost, remember, are those expenses which we can't necessarily allocate to the level of production. And so it's things like administrative salaries and accounting costs and advertising and insurance and warranty expenses. And so those are added on top of the direct costs. So there may be some factors which are related to the direct cost, which is actually buying the item and putting it in service, but then those indirect cost factors are over and above that. So I just wanted to emphasize that this is the equation that you should use for problem 7. Problem 8, then the formula that you should use is the cost capacity equation, which we're going to talk about that today as well. How differences in sizes aren't always having a linear effect in cost. So just a couple of hints for the assignment which is due on Wednesday. I guess problem 8 is also going to be incorporating the cost index on top of cost capacity. So I think our example today has the same thing, where it's cost capacity combined with cost index. And so cost capacity is describing difference in size for the item you have data for versus the item that you're building, whereas cost index accounts for the changes in expense over time. All right, so here's an aerial photo of something that if you've ever flown over a big city, you've probably seen something similar to this. It's not a bunch of swimming pools closely packed together, but it's a wastewater treatment plant. So kind of the opposite of a swimming pool, I guess. These are clarifiers. The circular things are clarifiers where solid waste sinks to the bottom of the tank and grease and foam rises to the top of the tank, and they scrape all of that out, and then they send the water from the clarifier into aeration basins. And in aeration basins, there is activated sludge, which is breaking down the dissolved pollutants. Before you discharge wastewater to the river, you have to send it through a treatment process like this to try and improve the quality of the water so that it's not causing problems downstream. So this is a really big one. This is probably for a large metropolitan area, and the cost data for something like this is going to be very different than if you're building a small wastewater treatment plant for maybe a remote rural community. So the differences in size are going to cause differences in cost. And the differences aren't always linear. This is the cost capacity equation, which says that you can predict the cost of some item number 2 if you've got the data for item number 1 by looking at the differences in size. And so Q here is talking about the capacity of, in this example, the capacity might be the flow rate of water that's being treated through a clarifier. Or capacity could be size of the item. Now, why it's important for us to have this correlating exponent is that there are some things that there are economies of scale where the more you buy and the larger the item, you're getting a bulk discount. So for example, if you're buying a rail car full of flour, it's going to be cheaper on a per pound size than if you're buying just a single bag of flour. And that's most things where there is what's known as an economy of scale. So the X, the correlating factor, is less than 1 when you're getting a cost advantage for the larger and larger, increasingly bigger sized items. If X is greater than 1, that's what's known as a diseconomy of scale. And there are a handful of things that the bigger it becomes, actually it increases the cost per unit rather than decreasing the cost per unit. So think about a skyscraper, and if you're building a very large residential tower, the taller it is, the more complex the construction becomes. And so on a per square foot basis, the cost of construction could be larger than a shorter building because of those diseconomies of scale. Another example of something for which there's a diseconomy of scale is a sludge drying bed. So, we were talking about wastewater treatment, and the solids that settle to the bottom of a clarifier sometimes are laid out on really big sand beds to be dewatered because that reduces the cost of disposal of the sludge if you dewater it. But a very, very large sand bed is more expensive on a per square foot basis than a relatively smaller sand bed because the access is more difficult, it's more costly to get an even distribution of the sand depth. So there's just a variety of technical reasons why sometimes items have a diseconomy of scale. And then of course if X equals 1, then that means that there really is no effect on the size. Of course, a larger item is more expensive than a smaller item, but it's a linear relationship when X equals 1. So if it's a linear relationship, then it means, for example, if it costs you $10,000 to build a swimming pool that has 10,000 gallons, then a 20,000 gallon swimming pool would cost you $20,000 to construct. That would be an example if you had a linear relationship in the cost capacity equation. So in this illustration, we're given data for a 5 million gallon per day water treatment plant. And so that is our Q1. We know C1 is $1.7 million. And Q1, the size of the item, or the capacity of the item, is 0.5 million gallons per day. We know the correlating exponent x is 0.14, so then that means that there is an economy of scale, a pretty large economy of scale. The smaller x is, that means the better the bulk discount you're getting. What we want to do is we want to predict C2. So we want to predict C2, the cost of the item, when Q2 is 2.0 million gallons per day. So if we put that into the equation, then what that tells us is we want to have C2, the predicted cost for the larger item, as the cost that we know, $1.7 million, and then the ratio of the sizes, 2 divided by 0.5, and it's to the power of 0.14. So anybody have their calculator handy today? And double check my calculations. I get, so 2 divided by 0.5 is 4, and then to the power of 0.14 gives us 1.21, and then multiply that by $1.7 million. I think that the cost of this larger plant is going to be $2.06 million. So it's kind of interesting. The first one, the small plant, cost $1.7 million, but we quadrupled the capacity of the treatment plant for this new one that's going to be built. It's 4 times larger, but it's only a little bit more expensive, $2.06 million instead of $1.7 million. So you see this in a lot of different fields, not just wastewater treatment, but if you're buying computer equipment, you sometimes can get like a much larger hard drive for just a little bit more money. You can see the reverse of that sometimes in equipment, where maybe a marginally faster processor is a lot more expensive. So that you can think of that as a diseconomy of scale, when to get 15% improvement in processor speed sometimes is double the cost for the processor. But this is really a powerful concept if we've got applicable data. And so there are analyses of every different field of construction and engineering, and this is just showing some of the correlating exponents for wastewater treatment equipment. And you could find similar data for residential housing construction. You could find similar data for automation systems that are used in automotive construction, manufacturing. So, this is showing that, for example, what we're looking for is maybe the extremes. A really low correlating exponent for like an aerobic digester. That means you can get a much larger tank for just a little bit more money. And then some of these are pretty close to 1. Like here, the laboratory correlating exponent is 1.02. So that means there's just a very slight diseconomy of scale if you're building a larger laboratory compared to a smaller laboratory. But then the really extreme diseconomy of scale here is for the sludge drying beds, where it's showing a correlating exponent of 1.35. So that means that doubling the size of a sludge drying bed is going to much more than double the cost. All right, let me hand you a copy of our in-class exercise for today. Let me just pull it up on the screen as well, this problem. Okay, we're going to combine 2 ideas together, just like you've got on the homework. We're going to combine together differences in size and differences in cost over time. Okay, so here we are going to try and predict some costs of a wastewater treatment plant. We've got data from 2010, and that was a small wastewater treatment plant where we knew the cost of the aerated lagoon, the blower, the pump, and we know the construction cost index back then. So this new project is going to be different because it's going to be larger and it's further forward in the future where things cost more money. So we have to account for both factors. We have to account for the increased cost due to inflation and the increased cost due to the differences in size. So in the second page of the handout on the back side of the paper are the correlating exponents. So what you should do here is find out what's the cost of the aerated lagoon, what's the cost of the blower, and what's the cost of the pump based on the differences in size and based on the shift of costs over time. In other words, the index. Let me just interrupt you for a second. I'll show you the calculations for the aerated lagoon, and then I'll pause again so you can complete the blower and the pump. Okay, so with the aerated lagoon, we know the size of the item we have cost data for is 2. The one we're going to build is 5.5. The known cost, 3.32 million. The correlating exponent we look up on the back side of the paper for the aerated lagoon is 1.13. So then, taking into account both the cost index, which is the passage of time, and the size difference, then that bigger aerated lagoon, which is going to be built in the future, is $12 million compared to the smaller one, which was 3.3. So we have to account for both of the factors, the inflation index and the size difference. Okay, so I've just put up the blower and the pump calculations as well. So overall, the cost of the project is going to be about $13.5 million. So, you know, even if you haven't crunched all the numbers yet, I think probably you get a sense for what the technique is and how it works, how this can fit together with the index method to account for differences in size. Let's continue on because we got to cover 3 different ideas today. The factor method, which I briefly talked about when I was giving you those homework hints, is just the notion that the cost of some projects can be estimated by multiplying them by a factor when you know a major piece of equipment and how much that usually accounts for the overall cost. So, for instance, when I used to live over in the United Arab Emirates, you didn't even really have to look at a restaurant's entire menu to know how much you were going to spend if you went to eat there. Like when I was in a rush and considering several different restaurants, sometimes I just look at what they charge for a bottle of water, because at a restaurant that charges $3 for a bottle of water, I could expect to spend around $30 at that restaurant. It just kind of, as a shorthand, seemed like the cost of the whole meal was about 10 times what a bottle of water would cost. And of course, that's just a rule of thumb. Sometimes you can get a lot more precise with real-world like construction or manufacturing cost data. But this idea is that the total cost can be represented by the cost of an individual component multiplied by some factor. So when you add in the indirect costs, then that further nails down the overall cost of putting something into service. So in the in-class exercise on the second page, it says that a new diesel generator will have a delivered cost of $975,000. Then we know the cost of pouring a concrete pad is usually 39% of the diesel generator's cost, and then training is 16%. And so what this formula suggests is that 1 represents the cost of the major equipment item, and then you add together the other direct cost factors. And so here in the example, the 2 direct cost factors are 0.39 for the concrete pad and 0.16 for operator training. So then multiplying that by the cost of the major equipment gives you the direct costs, and then the indirect cost factors are added on top of that to find the total cost of the equipment. So let me pause and allow you to estimate the cost of this generator installation project. All right, so $1.9 million. So that's a lot of add-ons, like you sometimes maybe have experienced this yourself where, you want to get new brake pads put on your car, and the pads themselves are maybe only $50, but then there's all these other things that really inflates the overall cost of what you're going to have to pay. And the same thing's true in this example where, the generator itself is just a fraction of all that it takes to get the thing up and running and connected and people trained. So $1.19 million, and that just illustrates the factor method. Okay, so just a review of some of the differences between direct costs and indirect costs. The direct labor is the labor which you can somehow tie into the cost of production, or the level of productivity, the number of things that are being made. So where the labor costs that are directly affected by how much you're making is the direct labor. There is some labor which is not direct, and those are the supervisory salaries and the labor which is associated with accounting and tax preparation, maybe safety training. The direct materials are the things that you're actually using the materials for building the item or for maybe the packaging. Manufacturing supplies. These are just all examples of things that the level of production is affected by those costs. And indirect costs are the overhead expenses that you have to pay, and they're inescapable. Even if you take a pause on production, you still have to pay all of these other costs. Because it's hard to assign indirect costs to a specific output, the question arises is, how do you account for indirect costs and how are you going to recover it? Because an organization that is manufacturing something sometimes doesn't know how they should get the money that's going to have to go to pay for supervisor salaries and advertising and so on. So it has to be allocated to some sort of a cost so it can be passed through to the end consumer. So for example, if one category is of indirect cost is taxes, like property taxes, then you might decide how much to, how to recover the money that's going to go towards taxes in terms of the amount of space that's occupied. And the situation where this comes up, like these kinds of questions, is usually when a company is making more than one thing, or if a company has more than one sub-organization in its structure. So for example, if a manufacturing operation is making both cell phone cases and also fidget spinners, for example, if the cell phone cases take up a lot of floor space in the factory, but the fidget spinners only take a really small footprint in the factory, then when it comes time to pay your property taxes, it would make sense that the fidget spinners shouldn't cover the same amount of the indirect cost as the equipment that's used for production of the cell phone cases. And so you'd look at the amount of space that's used by each of those to try and figure out like how much you're going to have to add on to the cost of the item, how much you have to pass through to the consumers to recover the cost of taxes. So there's all of these things: heat, power, receiving and purchasing departments, software, quality control, that you could have some rational basis for how the cost should be recovered beyond just like if you had 3 organizations within your company. You don't just divide the costs by 3. You have to look at how much of a certain thing they're using and basically try and tie their demand for the indirect category to the expenses you're going to have to try and recover through them. So the cost centers are the final products or services of a company. This is just some terminology that helps you to understand how budgeting is done in companies and organizations. And so it's a little bit counterintuitive, the name of this, because you sell your products. And so you'd think of it not as a cost center, but as like a revenue generating item. And of course it's both. A company is selling its products, but the products cost money for them to make. And so when they have costs, they have to tie the costs to the things that are being sold. So the cost centers receive the indirect costs, so that when you're trying to figure out how much to charge for the item, like the cell phone cases or the fidget spinner, it's not just the cost of the materials, but you're also recovering all of the underlying indirect costs as well. So the activities are the indirect cost processes that are causing the indirect costs. So we've talked about these a lot already. The supervising that gets done, the IT services that are provided to different subdivisions within an organization, and the cost drivers are the level of activity that drives the consumption of a shared resource. So the activities that are the departments providing support, there may be some sub-organizations that have a lot of packaging costs, for example, and others, maybe if one division of your company is producing software, which just can be downloaded by the consumer, and another part of your company is producing something physical that has to be packaged and shipped, then it wouldn't make sense to split down the middle the production and mailing costs for one item that's being delivered digitally and another one's being delivered physically. So all of these terminology and this thought process is meant to set up a structure for recovering indirect costs. So the last part of the in-class exercise on the second page, activity-based costing, we're looking at a hypothetical where, let's say there was a college that had 3 majors: computer science, safety technology, and engineering. Those are the 3 majors within the college, and they're very different in size, very different in the number of students they've got, how much computing resources they use, and the number of support calls per week that they send to the IT department. So if we knew that the college had to give $145,000 per year to the IT department, then there's a variety of ways you could do that. You could just divide the $145,000 by 3, because there's 3 majors, and have each one of the majors pay a third. But I think everyone would recognize why that's not necessarily fair, because some of the majors have more faculty than others. Some of the majors are generating more support calls per week. So what this last part of today's in-class exercise is asking you to look at is, what if you're going to recover the $145,000 on the basis of the number of support calls per week? So what you do is you add them all together. So the number of total support calls per week looks like is 13. So 13 support calls per week, then the engineering department should pay 5/13 times $145,000, and then that would tell you like their annual contribution, which is required to cover the cost. So I'd ask you to look at all three of these different ways of estimating the cost allocation: support calls, number of computers, and also the number of students. So which of these methods do you think the computer science department would prefer? Support calls, because they want to minimize how much they have to pay. So they'd say, well, we're only generating 2 support calls per week, so therefore we should only have to contribute $22,000 per year. Whereas if it was on the basis of computers, remember these are costs, then they'd have to pay $65,000 in the budget. So like, I guess, it would be administrative decision which basis, or maybe it would be a model that takes all of these into account. Because really, what are the activities that causes the IT department to be busy? Probably some of it is the support calls, some of it is addressing student questions and needs, some of it is keeping the computers imaged and up to date. So it might be maybe an average of different techniques in order to find out the true indirect cost recovery. But that's just a taste of several different methods that are used in the cost estimation. Remember that the assignment is due on Wednesday, and then we'll have a pause from the homework assignment so that you've got a little bit of extra time to finish up the project before it's due of Wednesday of next week.